Today in this video, we're going to be looking at calculating probabilities through simulations or through some sort of simulator. So the purpose for simulating is not just a single purpose. There can be other ways, but the purpose might be because of cost. That's probably a big one for a lot of them, or because of possibly ethical purposes. If you are going to simulate, say, a disease that people could be hurt from, well, that would not be considered ethical. Or if you were going to simulate, say, something with a plane crash, well, that's not really ethical or cost effective. So there's reasons why people would simulate probability once in a while. But for whatever the reason is, we want it to simulate reality, which then we can't forget about randomness. To say something to the effect of, 1% of, it would be less than that probably, 0.1% of airplane crashes crash. Well, you can't just take the number of airplanes times 0.001. You would, you could get that number, say, well, it should be on average that many. But of course, it could be a little bit more, or it could be a little bit less. So you have to be able to somehow still introduce randomness. And that's where simulations come in. It's not a simple, just straightforward calculation. It's a guided calculation, but we still are allowing randomness to enter in. For thousands of years, randomness was generated with either coins or dice. Dice were invented very early. The earliest ones found were about 5,000 years old, they figure, in the Iraq/Iran area over there. I don't actually know if these are any of the original ones. I tried to find images of the first ones ever found, and this image came up. I can't tell you if it's actually one of those or not. Romans, though, they used methods for introducing bits of information. Their way they did it was flipping a coin, similar to what we teach kids at young ages, flipping a coin, because, of course, that introduced randomness. They called it Navia aut caput, which means boat or head. So we do heads and tails. They did boat or head because the coin that they used, and it seemed like this one was a very specific coin just for this purpose, and maybe not originally, but it seems like they minted some of these just for doing this. I had a ship on one side and somebody's head on the other side. So boat or head. Like I say, similar to what we're doing. In the more modern age, when we're trying to have randomness for simulations, we have what are called random number tables, or at least we used to use these. Before the emergence of computers, statisticians who needed random numbers for random sampling and probabilistic experiments, they would make these really big tables. In fact, these things actually became valuable. Not that they are still valuable, but people would publish them in papers or even books, and then people would buy them so they wouldn't have to go through the work of trying to make them random. Now, I haven't seen it, but I was told a lot of these kinds of tables, and you have to imagine a book of these, it's just pages and pages of random numbers, that when they would create these, they'd come up with some physical way of making things so they would be random, and then they would write them down. And they had all these little schemes for how you could go about doing this. And that's why these ended up being kind of a money maker, because it wasn't necessarily easy to come up with. In modern age, we come up with random numbers typically one of two ways. It depends. For this class, the only way that you're probably going to, well, I shouldn't say that. You might use coins, dice, or maybe cards. But most of you will probably end up using an algorithmic simulator, something that uses an algorithm in a computer, aka your calculator, to simulate random numbers. And it's written with different algorithms in computer coding. Here's one example of one over here that I believe this is for the computer language C, if I recall. There's lots of these, though, that people have written. You're going to see this is a little bit of abstract algebra involved in programming here, and some stuff that you're probably really not going to understand, but it's a program for generating random numbers. There's also physical devices, which are way more difficult typically to use, other than, again, the coin, the die, or maybe playing cards or spin a bottle or something crazy like that. But in the actual sciences, sometimes they need physical, and they're actually required in situations of cryptography, lotteries, and gambling. There actually has to be a physical something, not just an algorithm written in computer code, a physical something that ensures that there's randomness involved. I found this here where there are a couple of Swiss scientists working on a way that light would go into your smartphone's camera here, and using quantum mechanics generate random numbers. Now you might go, why in the world would I want to do that? It actually has to do back here with cryptography. Cryptography is becoming a huge topic in the day and age we live with, because we buy and sell so many things online, and now we're buying and selling with our phones. And so keeping our money safe, keeping our private information safe has become very important. And part of keeping things safe is being able to generate random codes for keeping them safe for security purposes. And so I don't know if this one will ever happen. It's just a couple of guys that are working on trying to make something like that happen right now. But that would be an example of a physical device, so something that physically is random instead of just a computer sort of making decisions. I've got some steps here for making a simulation, and then we're going to get into practicing in a little bit. First of all, you got to clearly state what the goal is of the responses available. What do you want to find out? You're going to use a simulation to find out a number about something. What is it you want to find out? Identify the components to be repeated. Okay, so what are the moving parts here per se, if it was, say, a physical object? Explain how you'll model the components with a random outcome. Again, I know that a lot of you guys will probably use the random number generator on your calculator, which I'll be showing you in a minute how to use. But you still got to think about, how do you want to do that? Do you want to run the trial 1,000 times? Do you want to run it 50 times? How many times do you want to run it? And then do you want it to be a 50-50 ratio? Do you want it to be a 10% to 90% ratio? Yeah, you've got to be able to explain how you're setting up the components. What are equally likely digits? Events will represent what proportion? Okay, so when you get these digits out, what are they going to represent as you go through and make these? Explain how you'll combine the components to model a trial. In other words, when you're done, what have you answered? You got to run the trials, obviously. With computers, it's pretty much, you tell it what to do and you hit enter, but you still got to have it run the trials. And then, of course, you can collect and summarize the results. Maybe you're doing it many times. When it says to summarize, we're talking about the shape of the distribution, the center of the distribution, the spread of the distribution. It should start to sound familiar now in the statistics class. So you'd want to not just give a number when you run several trials, but start to actually describe what it looks like. Shape, center, spread. You might want to put that in your notes. And then, of course, you'll need to state your conclusions. If you have conclusions, you're going to want to write those down based on what you found out. So let's take a look at a simulation. I am not going to make you to use a simulation table. This is, like I said, something that statisticians did 100 years ago. They had all these tables. I'm not going to have you do that. But let's simulate a procedure and a process that behaves the same way as the real life procedure would result in. Okay, so the example here, I want to do a simulation with the births of 120 babies. Okay, well, we know that it's approximately 50-50. So this is where you have to be careful not to just throw out a calculation. Say, well, the ratio is like 50-50, so it should 50% of that 60, so it'd be 60 boys, 60 girls. You just created a calculation, and by doing that, you totally remove the possibility of randomness. I would say that if you go to a hospital and actually start, say, keeping data for a month, you're going to get really strange results on certain days. Some days you might get close to the 50-50, but on other days maybe you get, all girls born in one day and no boys. You're going to get weird results in real life to random events. So we have to be able to simulate that. How do we get this to happen with approximately that, but allowing for randomness? Even though the law of large numbers says that within many trials you should approach 50-50, the real life, again, this is what I was just saying. We know that we're most likely would not end up with 60 and 60. Of course, you look at 1 million births, well then, yeah, you're going to be close to that ratio there, but not out of just 120. So here's an idea. This is okay, how could I simulate this? Maybe just flip a coin. That's pretty straightforward because it's 50-50. So this is the part you got to think about. What's the ratio that I'm expecting? How could I simulate something that gives me a similar ratio but allows for randomness? Obviously, flipping a coin would allow for randomness. Or, like I said, we could use a random number generator. Maybe you just have it spitting out maybe just ones and twos, where the boys would be the odd number, so the 1, and the girls would be the even number, so maybe a 2, and you could repeat that 120 times. And then, of course, you would count up how many boys you got, how many girls you got. You could then look at the shape of the distribution, the spread, which this one wouldn't be super interesting. It'd be pretty straightforward here. It'd just be how many boys, how many girls. But then you could maybe draw conclusions off of that. You can run random number generators in your calculator. Let's do an example here. Say you wanted to generate the sum, so I'm going to add them together, of 2 dice. Now realize you can't get a 0, you can't get a 1. If you throw in 2 dice, the least you can get is a 2. The most you can get is a 12. Snake eyes, 2 1s would give you a 2, and of course 2 6s give it a 12. And I want to get the results of doing this 10 times. So there's my procedure. What you would do with your calculator is you go to your math button, go to probability. It's you're going to have to arrow over on that. It's about the 4th pull down menu, I believe, to the right. And then you're going to find random integer. That's what this stands for, RAND, random integer. In the older calculators, you're going to put this in. You're going to go parentheses 2, 12, 10. What you're looking at is the lowest number, the highest number, and how many times am I repeating the procedure. Not many of you probably have the old black graphing calculators. They're not around much anymore. Most of you are going to go to your random integer, which is right there, and you're going to hit enter, and it's going to ask you for the lower number, the higher number, and the how many times do you want to repeat it. And then you'll hit enter, and it'll start to spit these out. Now, if the list is long, it's going to go off of your screen. You're going to have to use your arrow buttons to keep moving over to the right to get all of the numbers. And there's a list of 10 random integers between 2 and 12. Now, this is a little trick here to keep in mind that you might want to do this once in a while when you're actually analyzing them, is to be able to store your list so that you can later go back and sort your list. Okay, so store on your calculator, you've got a store button. It is down towards the bottom on the left, right above the on button. And then you'd want to hit 2nd and 1. Okay, so what this would do is store it in list 1. Above the number 1 on your graphing calculator is L1. And so what you're doing is you're storing it. So you'd hit store, and you'd hit your second in list 1. So you're storing it in list 1, so it's going to be in your stats part. So I got some random integers here, and I'm going to store them in list 1. And this is a lot of them. Notice there's an arrow going off to the side here. There's a whole bunch more to that. Going from 1 to 365, and I'm repeating this 25 times is what's going on there. Once you've got them stored in list 1, then you can go to your stats and hit sort list A or sort A. Make sure it's sorting list 1, and it'll sort them for you. So it'll take them and it'll sort them for you. I've got right there. There we go. Now I've got them sorted in list 1. And in this case, it's going to go from the lowest to the highest. And so it makes it a lot easier now to start to talk about things like the shape of it. What's the lowest? What's the highest? What's the mode, the thing that's repeated the most often? It's really difficult to do when it's just these numbers like this. So to store it into a list, sort it, and then be able to look at it, and you have to scroll down here because remember there's 25 of these total. To scroll down and be able to look at them is a very handy feature. This one, notice, stopped. The biggest number was 360. Did not actually get to 365, but that's okay. Now I want to show you what you were looking at here. If you recall when we talked earlier about the multiplication rule and we talk about the birthday problem, we were looking at the birthday problem, which was there was this probability problem related to if you had 25 people in a room, the probability of at least, and that was the term we were looking at the time, at least 2 of them having the same birthday. If you recall, that was the problem we looked at, and that's what I actually just calculated here. I simulated that. I simulated that problem. So out of the 365 days, so from the first day to the 365th day, picking random numbers 25 times. When I've got them sorted here, notice here, right there, I got 2 people with the same birthday. The 3rd day of the year is what that would represent, the January 3rd. And so that would be a way of simulating it. So I actually got one to show up. It was random, but if you recall, when we did that problem, there was a 50% chance, in fact, slightly over 50% chance that if you have 25 people in a room, that 2 of them are going to have the same birthday, day and month, not necessarily the same year. Here's another. We did the activity with the random walk. I'm going to do that same thing, except instead of a coin, I'm going to use a 1 to be the head side of the coin, 2 to be the tail side. But I'm going to repeat this 200 times. So lower 1, upper 2, repeated 200 times. And here we get started. Here's a run of 5 hits. If you recall when we did this, people got some strange runs of numbers. Again, that was the whole point of showing that with randomness, you don't always get what you would expect. Here you got 5 heads in a row, which can happen. We saw that when we were flipping coins, that, you know, it starts to feel weird once you get 3, 4, or 5 in a row. You're like, wait a minute here. I've got the same thing every time. But it does happen when true randomness is allowed to work. There's a run of 6 heads. I even ended up with a run of 8 tails. When I did this, I sorted it. Of course, there are 200. I had to sort through. I had to look at them all here. But I ended up with one time a run of 8 tails, which very much so fits some of the things we saw when we did that little activity with the random walk. All right, let's get back to creating simulations. So here's a situation. Let's say that we've got this factory producing parts, and they know that on average they have 1 bad part for every 50. And they want to look at a probability model without actually making them and making all the bad parts. But they want to look at a simulation for simulating the production of 300 parts. How could you go about doing this? Well, you could think about coins. You could think about, a coin wouldn't be great necessarily because it's kind of a 50-50. A die, if it's a 6-sided die, well, you could think of ways you even odds, but that's really limiting you there. You could obviously use the numbers themselves. I suppose if you had a 50-sided die, which I don't even know if they make such a monster, but if you had one, well, then you could do that. You could assign one of the numbers to be the bad part and see how many, out of 300 rolls, how many times you got a bad part. Or simply, we could just do this. Since it does go through the cycle 6 times, I'm talking about taking 300 and dividing it by 50. That's a cycle, 50 at a time, on average 1 bad part per cycle. Then what we could do is we could go 1 to 50 on our random number generator on our calculator, and we could repeat that procedure 6 times and just see how many times a 1 shows up. Maybe none of them show up. Here's another example, and this is definitely now when you get into the medical things where simulations are wanted, at least with certain things. Describe a procedure where you could enter into a calculator 20% expected infection rate in a city. Okay, so people are getting sick from something. With a sample of 50 people, each of the 50 outcomes should indicate one of two results, that being either that they are infected or not infected. Here again, this is not a good one for flipping a coin because it's not a 50-50. It's a 20%, so 20 out of 100 or 10 out of 50 if you want from that. But it's a 20% rate, and we want to repeat this 50 times. Well, how could I do that? And again, you got to be creative with these sometimes. You might have to sit there and stare and think about it for a while to figure out how you could possibly do this, but this would maybe be one way to do it. On your random number generator, have it generate numbers, and if it lands on a 1 to a 10, we can say, well, those people are infected. So if I got a 7, well, that's an infected person. But then if it lands anywhere from 11 to 50, we can say, okay, well, that's not infected. So this gives me that 20%. That would be the rate I would get. And so I'd have it going from 1 to 50, and I would repeat that process 6 times and see what happens. There are also, and there's a lot of these things online, there's a random number generators. So here's an example of one here. This is an easy one to use. That's why I'm showing this to you. If you want, it's under Digital First. Honestly, if you just start Googling around for random number generators, you're going to find something. In this one here, it's set up right now to do a coin toss. The probability of heads is 50%. So this would be your standard coin toss. And you could, well, I want to repeat that 15 times. So you go ahead and toss it, and it goes through. And what ends up happening, really don't know. Okay, so there we go. And if you want, you can toss it again, and you could keep going. So now what should do? Get up to like 30. And now you can see show true probability. Okay, so the theoretical one. Notice this is kind of like when we did our random walk. It's actually below it quite a bit, but that's random because we don't know what it's going to end up being. Now, you don't have to do this. Say we wanted to do that 20% infection rate. What we could do is we could take it down to 20%, and we wanted to have it be for 50 people. So there's 50. So let's reset that. And we could go through right here. And see what happens. Oh, it touched 20% there, but it's not going to land on 20%, I don't think. No. Okay, so it landed at a little bit higher. So 13 out of 50. So here's the results. 26% when we let randomness do its thing. So yes, in theory, it was infecting 20% of the population, but out of the 50 people, well, it ended up with 26%. Now, law of large numbers says, hey, if I start to do this a lot, then eventually it will start to float closer to that 20%, but not necessarily when you expect it. When I say a lot, I mean, it might have to go into the 10,000s or 100,000s to get it to get there. It's kind of just staying above right now. It actually hasn't gone below, I don't think, yet. But that's how this simulator can work. So you could just keep on going and going and going if you want it. And again, you can always end up, oh, there, just barely over 20% now. Just dropped at the end there of what it's going to be. So you could use one of these. It's a great way to do some simulations. It's all programmed for you, easy to use. And that's a nice, now it is a programmed one. It's not a physical one. It's obviously it's simulating something physical, but it is just an algorithm. So I want you to try one here. I want you to think about this. The American College of I'm not even going to try that today. Say that out of 100 babies born in the United States, 3 have some sort of what's referred to as a major birth defect. Now, obviously, there's ethical reasons so you can do a study where you're looking into the past. That would be different. But if we want to somehow make some sort of prediction and we want to assign random numbers, obviously, this is the perfect situation for a simulation. So we've got a 3% rate here is what we're talking about. And here's what I want you to try. if you think about times when we've had a guest speaker come to school and got everybody sitting up on the stage there, and one of these motivational speakers, maybe they're coming to school talking about major birth defects, and they want to randomly have people stand up to imitate people that have a major birth defect. Okay, now I picked a school our size here. In fact, these are the numbers from our school. This represents 9th through 12th graders, 588 students. And, again, I don't want just a calculation. I don't just want 3% times 588. We want to allow for randomness. How would you set this up so that it falls around that 3%, but we allow for randomness to know how many students there should be approximately? And that's going to be one part. And then, so the other part is selecting the students. So here's the simulation I want. A randomly proportionate, okay, so proportionate meaning that 3%, sample size of students chosen to represent the 3 out of 100. This will be hard. This will probably be the harder thing. Second, once the number of students has been chosen, how could you have the students be randomly chosen? Say, that girl right there, or, that boy right there. How could they be randomly chosen? I want you to pause and I want you to think about this. How could you do this? Is, again, 2 parts here. Okay, I don't know what you came up with, but maybe one thing would be to go back to that computer random number generator that I just showed you, because you could set it up to have a 3%, right? And you could run it obviously just 100 times. Oh, excuse me, you could run it 588 times and see how many you actually come up with. It probably is not going to be exactly 3%. It might be in the ballpark, but probably not exactly. So then you'd have your how many, and then I have no idea. Maybe each seat has a number on it. Somebody's gone through ahead of time and taped numbers to all the seats. I know this would take forever. I'm just throwing out ideas here. And then you grab your calculator, and whatever the number that you get from your random number generator, then maybe you have the calculator select that many out of 588. So you'd set it from the low end of 1 to the high end of 588, repeated so many times. Of course, there's a possibility you're going to get a run of the same number. Well, you can't have that. And so then you'd have to decide how you're going to deal with that. Either run it again or just not include that one. But I don't have necessarily the solution. I'm trying to get you to think of possible solutions, possible ways of solving this problem here. All right, so here's some problems for you to try. Obviously, you're going to want your graphing calculator available. Have a good day.